All right, let's jump right in. Today, we're tackling one of the oldest and deepest questions in all of science. What fundamentally is light? It seems so simple, right? But its true nature is this fantastic scientific mystery that took centuries to unravel. So here's how we're going to crack this case. We're going to follow the clues just like the scientists did, starting with a simple idea, then bam, we hit a major plot twist, then another one that deepens the mystery, and finally, we get to the incredible truth about what light really is. Okay, so let's dive in. For a very, very long time, scientists had this beautifully simple way of thinking about light. And it's a model that you and we use it intuitively every single day without even realizing it. They called it the ray model. The idea is super simple. Light just travels in perfectly straight lines. Think of them like tiny, super fast arrows shooting out from a light bulb or the sun. And you know what? This model is actually amazing for explaining a ton of the stuff we see all around us. Take reflection, for instance, or riflessione, as it was called in some of those early scientific papers. Just picture a tennis ball hitting a wall. It bounces off at the exact same angle it came in at, right? Light does the same thing. It's that simple. And that's why mirrors work. It's how we see pretty much anything that doesn't make its own light. The ray model also totally explains why light sometimes bends. You ever notice how a straw in a glass of water looks kind of broken right at the surface? That's refraction or rifrazione. See, when light goes from the air into the denser water, it slows down a bit and bends. And this isn't random at all. It's so predictable that there's a math rule for it, Snell's law. So for a while there, it really seemed like the ray model had it all figured out. It was neat, tidy, and it worked. But as scientists started looking closer with better tools, they began to see some really weird things, behaviors that a simple straight-line ray just couldn't explain, not at all. And that leads us right into the first big plot twist in our mystery. A totally new theory popped up, and it suggested light wasn't a ray or a little particle, but something completely different. So back in the 17th century, you've got this physicist, Christian Huygens, who comes along with this wild idea. Huygens said, hey, what if light doesn't travel like a ray, but like a wave? You know, like when you drop a pebble in a pond and the ripples spread out? Huygens believed light did the exact same thing. But the real knockout proof for the wave idea came from Thomas Young's amazing double-slit experiment. Now think about it. If light was just a stream of tiny particles, like microscopic baseballs, and you shot them through two slits, what would you expect to see on the wall behind? Two simple stripes of light, right? Makes sense. But that's not what Young saw. Instead, he got this bizarre, intricate pattern of many bright and dark stripes. And that was something only waves could do. This interference pattern was the smoking gun. There was no other way to explain it. As the light waves passed through both slits, the new ripples started messing with each other. When two wave crests lined up, they amplified each other. Boom, a bright spot. But when a crest met a trough, they canceled each other out, creating a stripe of pure darkness. And just like that, it was done. The debate was over. For almost 100 years, the entire scientific world was convinced the mystery was solved. Case closed. Light is a wave. Or was it? Yeah, but physics is rarely ever that simple, is it? Just when everyone got cozy with the wave theory, a totally new experiment came along that threw everything back into chaos. This was the second, and honestly, even bigger plot twist. Okay, so this thing is called the photoelectric effect. Here's the deal. Scientists found that if you shine light on some metals, you can actually knock electrons right off of them. Now, the wave theory said that any color of light should work as long as you make it bright enough. More brightness means more powerful wave, right? But that's not what happened in the lab. A dim ultraviolet light worked just fine, but a super intensely bright red light did absolutely nothing. Brightness didn't matter, only the color, the frequency of the light did. The wave theory had no answer for this. This head-scratcher was finally solved by the one and only Albert Einstein. He proposed something that brought the particle idea back from the dead. He said light isn't a continuous wave after all. Instead, it's made of individual, separate packets of energy. He called them photons, or photoni. It's simple, really. A blue light photon just has more energy packed into it than a red light photon. And to knock an electron loose, a single photon has to have enough energy to do the job all by itself. It's like a one-hit knockout punch. So now, physics was in a real bind. I mean, look at this. You have Young's experiment, which proves light is a wave. And then you have the photoelectric effect, which proves it's a particle. How can it be both? The evidence was completely contradictory. It felt like science itself was broken. And this leads us to the final act of our mystery. How do we solve this paradox? Well, it turns out the answer isn't one or the other. And what it reveals is something truly profound about how the universe actually works. The answer is wave-particle duality. It's mind-bending, but here it is. Light is not a wave, and it's not a particle. It is both at the very same time. It has properties of both, and the face it shows you just depends on what kind of experiment you're doing. It's one of the weirdest but most fundamental rules of quantum mechanics. And you can see this duality all around you. You see light's wave nature every time you see a rainbow. This effect, called dispersion, or dispersione, is what happens when white light hits a prism or a raindrop. It splits into that beautiful spectrum because the different colors, which are really just different wavelengths of light, all bend at slightly different angles. That is pure wave behavior. And then you can see light's particle nature every single time you look up. Why is the sky blue? It's because of something called Rayleigh scattering. As those little packets of sunlight, those photons, zoom into our atmosphere, they start crashing into air molecules. The high-energy blue photons scatter all over the place, way more than the lower-energy red ones. It's that particle-on-particle collision that literally paints our sky blue. So in the end, light just refuses to be put in a neat little box. Depending on how you look at it, it shows you a different side of itself. Sometimes a wave, sometimes a particle. It's a powerful reminder that the universe is often way stranger and more wonderful than our everyday senses can grasp. And it really makes you wonder, if something as basic as light can have this bizarre dual nature, what else about reality isn't nearly as simple as it seems?